Molecules indeed have shapes. Like for example, methane is tetrahedral in shape. And the shapes of the molecules influence their physical and chemical properties. In chemistry, it becomes necessary many times to be able to predict the shapes of the molecules. Now, in this short video, we are going to look at a very simplified theory that is called as the VSEPR theory, which stands for valence shell electron pair repulsion theory, which was proposed somewhere around 1950s, and it was successfully used to predict the shapes of the molecules. Now, to understand this theory, we have to understand what is meant by valence shell. Valence shell means the outermost shell of an atom. Now, when we have to predict the shape of a molecule, we look at the central atom in a molecule and determine the number of electron pairs surrounding it. Then we work out the best possible arrangement for these electron pairs such that they are furthest distance apart, so that there is minimum repulsion due to having the same charge, and therefore they have maximum stability. Now, to understand how this theory works, we can consider a simple molecule like beryllium fluoride, and let's try to find out what shape this molecule might have according to VSEPR theory. So first we look at the central atom. It is obvious that the central atom in BeF2 is Be, beryllium, and it is surrounded by two fluorine atoms. So to apply this theory, we look at the atomic numbers of the atoms. So the atomic number of beryllium is 4 that we can find from the periodic table, and fluorine is 9. Then we look at the electronic arrangements. So for beryllium, it will be 2, 2, and for fluorine, it will be 2, 7. And now we have to only consider the outer electrons, 2 electrons of beryllium and 7 electrons for fluorine, which will take part in bonding. So now let us use dots and crosses to represent these electrons. So beryllium has 2 electrons, as you can see. Beryllium has 2 electrons, and we have shown these 2 electrons by 2 crosses. So beryllium is surrounded by these 2 electrons. Now fluorine has 7 electrons. So the electrons of fluorine have been represented by dots that you can see, 1, 2, 3, 4, 5, 6, 7. And similarly for the other fluorine, 1, 2, 3, 4, 5, 6, 7. Now let's see how many electron pairs surround the central atom. So as you can see that beryllium is surrounded by 2 electron pairs. Now let us see how this knowledge can help us to predict the shape of the molecule. So when we have 2 electron pairs which form 2 covalent bonds, now let us use straight lines to show these bonds, and then try to find out the possible arrangements which might occur for beryllium fluoride. So I have used straight lines to show the 2 covalent bonds formed by beryllium. Now you can see 4 possible structures, even though there can be many others possible. Just for example, we are considering these 4 structures. So the 2 fluorine, the bonds of beryllium with fluorine can be arranged in this way, or in the second manner, or third or fourth, in which different bond angles have been shown between the fluorine, beryllium and fluorine atoms. So the bond angles might be 90 degrees, somewhere around 45 degrees, 120 degrees or 180 degrees. Now, which structure out of all these four will have minimum repulsion between the electron pairs so that there will be maximum stability? It's obvious that the fourth structure in which the bond angle is 180 degree, F bond angle is 180 degree, is the arrangement in which these electron pairs are as far apart as possible, because the angle is maximum, whereas in the other structures the bonds are closer together, so there is bound to be more repulsion than in the structure represented in 4. So the VSEPR theory predicts that the shape of beryllium fluoride will be linear and the bond angles will be 180 degrees. And fortunately, this is found to be true. So this is how we have tried to understand how the electron pairs will arrange around the central atom to give molecule maximum stability. So beryllium fluoride is found to be linear in shape and the bond angles are 180 degrees. Now let's consider another example, that of methane. Now the central atom here is carbon, whose atomic number is 6. So the electrons are arranged as 2 and 4. The peripheral atoms are the hydrogen atoms, whose atomic number is 1 and they have just 1 electron. Now once again, let's draw the electron structure of methane, in which the electrons of carbon have been represented as crosses. So there are 4 crosses around carbon showing the 4 electrons in its outer shell. Then there are 4 hydrogens. Each hydrogen contributes 1 electron in the overall structure. So once again, looking at the central atom, which is carbon, and then just counting how many electron pairs surround the carbon atom, we can immediately see that there are 4 electron pairs which surround the carbon atom. Now, once again, we are faced with the same question, that how these 4 electron pairs can be arranged so as to be maximum distance apart, so that there is minimum repulsion and maximum stability. So once again, to simplify the matter, we can show these bonds, these covalent bonds, by straight lines, and then we can arrange these 4 bonds around carbon in various manners, showing different bond angles, and then look at the structure and find out the structure in which the bonds are maximum distance apart. And one arrangement could be something like this, that the bond angles are 90 degrees. Another arrangement could be in which the 4 bonds form a tetrahedral arrangement where the bond angles are 109.5. The normal lines indicate the bonds which are in the same plane. The wedge shows that the bond is coming forward, and this kind of wavy line shows that the bond is going behind the plane. And this is in the shape of a tetrahedron. This is a 109.5 degree angle, and these angles are exactly the same whether you consider this bond or this bond or this bond or any other bond. All the bond angles are 109.5 degrees approximately. And this is the arrangement in which the electron pairs are maximum distance apart from each other. You cannot have a better arrangement in which the bonds around carbon are distributed farther to one another than the arrangement which has been shown in the tetrahedral arrangement, which means that this is going to be the most stable arrangement of the hydrogen atoms around carbon. And that is predicted by the VSEPR theory, that the electron pairs tend to be maximum distance apart to give the molecule maximum stability. Hence, our prediction for the methane molecule is that it would be tetrahedral in shape and the bond angles would be 109.5, which is in fact found to be the case. So we once again find that by applying the simple principles of VSEPR, we are able to predict correctly the shape of methane molecule. Then if we go on looking at some other examples, then this is what we can find. We can make a short table in which we can consider the various number of electron pairs. Remember that we are talking about electron pairs rather than simply the electrons, because the electron pair forms a covalent bond. So if we count the number of electron pairs surrounding the central atom and not just the number of electrons. So if the electron pairs around the central atom are 2, as we found in our first example, beryllium fluoride, then the molecule becomes linear in shape, and the bond angle between FBEF, this bond angle, is 180 degrees. Now, if there were 3 electron pairs surrounding the central atom, as in the case of boron trifluoride, each covalent bond represents an electron pair. So boron is surrounded by 3 electron pairs, and these electron pairs tend to be maximum distance apart, which can be achieved by making the bonds in such a way that the bond angles are 120 degrees, whichever bond we consider, and this shape is called trigonal planar. Planar because all these 3 bonds are in the same plane. And this is the arrangement in examples like boron trifluoride, as well as other examples like BCl3. And then, of course, we already considered that what happens to the shape when there are 4 electron pairs that we saw in the case of methane. And we found that the best arrangement, which gives maximum stability, is a tetrahedral arrangement where each bond angle is 109.5 degrees. There could be other examples, like for example carbon tetrachloride CCl4, which will also have the same shape. Now, if we go to a molecule which is surrounded by 5 electron pairs, as in the case of PCl5, then the best possible arrangement is a trigonal bipyramid arrangement, where the 3 chlorines are in the same plane, and one chlorine is in the upward direction and the other chlorine is in the downward direction. Now, when you consider the bond angle between the Cl, PCl, which are in the same plane, that is 120 degree, and the angle between the chlorine projecting upwards and the chlorine in the plane, that angle is 90 degree. Similarly, another example, if the central atom is surrounded by 6 electron pairs, as in the case of sulfur hexafluoride SF6, the arrangement would be octahedral, where 4 of the fluorine atoms are in a plane, and one fluorine is projecting upwards and another fluorine is projecting vertically downwards to the plane, and each of these angles is found to be 90 degrees. In this above discussion, we have just taken some very simple examples to illustrate how the VSEPR theory works. But of course, we can have more complicated examples where we can consider the presence of lone pairs of electrons. The lone pairs of electrons are those electrons which do not take part in bonding. And this alters and modifies the shapes of the molecules that we predicted on the basis of this simple theory. And I will be doing another video in which I will explain how we determine the shapes of molecules which have bond pairs of electrons as well as lone pairs of electrons. I hope that you understood the simple introduction to the VSEPR theory. Thank you very much.